Okay, let's get started. Um, all right, so last class we talked about power iteration, the analysis, how it depends on the gap, and some various tricks and variants of it, like for example, how to include momentum in it, subspace iteration, how you can play around with it to try and get the least singular value if you wanted to without computing everything, and so on. So today I'll discuss a new application to matrix completion, and then we'll start talking about a new topic, which is privacy. Okay. All right. And a couple of announcements. First, homework 2 is due today at 10 p.m., right? And more importantly, exam 1 is on this Wednesday. And this covers lectures 1 through 9. Okay. So exam 1 is on this Wednesday, in class lectures 1 through 9. And the format will be similar to the previous year's exams, maybe a few problems and then a few multiple choice questions. And as I said, you can bring one handwritten page. Don't go too overboard with it. I don't think it's going to be that important. In the sense that don't rely on it fully. Try to understand the main concepts and algorithmic ideas. Okay. All right. So we were talking about the power iteration. And let's just recall the main thing that we said. Well, okay. Anyway, it's not copying, so let me just say. So the two main properties of power iteration were PI converges depending on the gap, right? And if the gap is epsilon, you roughly need around 1/epsilon iterations to get a vector which is very close to the first singular vector or to the span of the first singular vector, depending on the gap. And the second one, which is a very important computational property, is that we only need to be able to do matrix vector products. Okay, so we only need to be able to do matrix vector products to actually run through the power iteration. Okay, so for the next assignment, you will implement a few of these things, and you'll clearly see that our theoretical bounds will match the empirical performance very tightly. Okay, there are a few cases where you can maybe beat it empirically, but pretty much in every case, the theoretical bounds are very consistent with what you're observing. Okay. All right. And towards the end of last lecture, we were talking about potentially using the fact that we can solve the low rank approximation problem, not just for itself, but for the matrix completion problem. Okay, so let me just describe that in a bit more detail, and then we'll move on to the new topic. Okay. So just to remind ourselves, so what's the matrix completion problem? We have this big matrix, think of it as users and movies, or items and users, and you want to give recommendations. right? And of course, most of the entries are not known. And our goal is to kind of build a model for the missing entries. Right? Sometimes you might not even have the ability to write down the entire matrix, but you want to have a model which says, okay, here's a user, here's a movie. Tell me what is your expected prediction for the rating, okay? And the way we abstracted it out earlier is, we have some set theta is subset of n by d. We have n users, d movies is the set of scene entries. Okay. Think of this as being very small. So for example, in the Netflix challenge, the size of this set over the total size was roughly something like 0. Okay, typically it's even smaller. Okay, and we said one way to try and model or try and make a prediction is you have to come up with some simplifying assumption about the true matrix. And one natural assumption which gives you some good improvement by itself is low rank approximation, right? So we can model this as the following problem: input entries of x in theta, and our output, we want to find a matrix x hat of rank less than or equal to k. We have some rank bound k, and our goal is to do okay, and this is the matrix completion. Right? And in general, this problem is actually NP hard. It's kind of a little bit non-trivial to show it, but you can show that this NP hard. And it's even NP hard to get all kinds of approximations for these things. But there are some cases where you can actually solve it. For example, if the set of entries theta is chosen at random. So if you imagine that each user rated a random subset of movies, then you can actually solve it. But in practice, that's not the case. I'm not just going to watch a random subset of movies and rate them. The choices are kind of correlated with each other. Yeah, for sure. Yeah, basically, think of it as I want to get epsilon close to the optimum value. Okay. Yeah, in the case of theta being random and x has some non-degenerate assumptions, you can do that, right? So for example, if x has one, is kind of a matrix where a few entries which are non-zero and everything else is zero, you're not going to see the non-zero part, right? So you cannot get exact recovery in those cases, but you can at least hope to get close to the unknown matrix in some cases, okay? And there's a lot of work on this problem, trying to get algorithms which have provable guarantees, because it also connects to many other problems across learning theory and even in optimization and in classical algorithms, right? But in general, that's a big caveat. Like assuming theta is random is a strong assumption. Okay. Right. And in fact, at some point when I was in grad school, I did some experiments with the Netflix dataset, and you can see that the sampling is not at all random. It has this power law distribution in terms of how many users with how many movies. There are a few users who have rated so many more movies than most other users combined. So you have to take all of those things into account. Okay. And same for movies. Few movies get way more ratings compared to others. All right. But anyway, so we are trying to develop some heuristics or some reasonable algorithms for this, right? And one thing we said was just kind of substitute the missing entries with the averages and do SVD. That gives you a good starting point, but you cannot, it's a starting point. You want to improve that further. If I give you more time, more compute power, can you improve it further, right? And this is where we said we could potentially use the loss minimization, or basically write it as a loss. Right? Among the known entries, give me a matrix such that its values are as close to the values in the known entries, okay, while this matrix is simple. Right? So I can say, our goal now is to minimize this loss function subject to rank of y less than or equal to k. Okay. So this is a constraint optimization problem. Several lectures ago, when we said if you have a constraint optimization problem, one of the things you can do is projected gradient descent, right? But in general, computing the projection operation is tricky. And here also, it should be tricky. And in fact, the analysis doesn't work. But nevertheless, because of the magic of SVD, we can do the projection operation, right? So, meaning, if you think of this set of low rank matrices, it's a highly non-convex set. Nevertheless, if I'm anywhere here, I can take a gradient step. Once I go out in projected gradient, we would like to come back to the set, right? And projection for us is computable in this particular case. There are very few non-convex sets for which we can do the projection operation. And low rank matrices is one of those very special and very useful sets. Okay, so for example, let's say of y is let me just not write this. It might be confusing. Okay. For any matrix y, I want to find the matrix which is the best low rank approximation, right? And this is in the Frobenius nominator. Okay. And this we know we can solve, can be solved by SVD. Okay. So we can now try and run projected gradient descent. Even though the standard analysis doesn't work, you can at least implement. Okay. And you can show that it gets pretty good guarantees in general by working harder and making some slightly different assumptions. Okay, this is a paper that I had long ago. So you start out with y0. Think of y0 as maybe just SVD of x preprocessed. Right, so this is the first step we discussed. In Netflix challenge, if you just did the pre-processing and SVD, you got a 4% boost. Let's say that's what you start out with. And then we say yt prime is yt minus 1 minus. Okay, I'm taking a gradient step. I have my loss function. I do the gradient step. I get a new matrix. And then my next iteration is the projection, which is best rank k approximation. Okay. And this works quite well in many cases. In fact, if you take a reasonable matrix X and you sample entries theta at random, right, then it recovers the original X in very few iterations at an exponential. It works really, really well. Even when the number of seen entries is something like theta of n times k log. Okay, so very efficient. Like, n times k is just to write down a rank k factorization. With log n more entries, you are able to actually recover the entire. Okay, which is quite cool. We don't have the proof of such a strong guarantee, but empirically does achieve this. There are various analyses which can show something like this, which like nk polylog and some other additional assumptions. Okay. All right. Now, so this is a nice enough algorithm, gets good theory guarantees, but you should wonder, how would you actually implement? Think of the scale of the Netflix data set, right? Now, so let's say, this YT is low rank, so that part is fine. And we can never write down a full matrix, right? But if these YT primes are getting like full matrices, these are no longer sparse, right? So how would you, kind of implement it? Because we cannot write down a full n by d matrix in our RAM. It's almost 10 GB or 8 GB of RAM. So how do you get around that? But what representation would you use at every step? You're almost, yeah? Right. So basically, you write it as a low product of two low rank things, plus the gradient is a sparse matrix. So you really have to kind of go in and hard code this matrix vector multiplication. It's not even just like I have a low rank matrix and multiplying it with vector. So one thing that's important to exploit is to say that, so YTs are all always low rank, okay? But we never multiply it. Like we never write down YT. We always keep track only of the SVD of the matrix. Does that make sense? So we basically only keep it as something like, UT times sigma T times VT, right? With only K non-zeros, basically. Okay. So you have to keep this invariant because of computational things. I can never write down this full matrix. I have to keep U, sigma, V separately. Okay. And then the other thing is the gradient is a sparse matrix because what is the gradient of L? Right? So the gradient of L only depends on the entries in theta. Okay. So the gradient is basically 0 at any entry that you do not see. Right? So you have to exploit that in your representation as well. Because the gradient L is non-zero for, sorry, is 0. Or maybe you can say it this way, is non-zero. Okay, so gradient of L is a matrix which basically has 99% of the entries are 0. Okay, so you keep track of these two things. I have a sparse matrix, and then I have this low rank matrix, and you have to keep multiply them properly every. Okay, so you kind of implement how do I keep these two things separate. If you add them up, you lose the sparsity and the representation compactness. Okay, so knowing kind of how it works is helpful in actually implementing. Okay, any questions about this? Yeah. Mm-hmm. Oh yeah, okay, so this should be right. Maybe that is a good point. So let me write it properly. It's actually something like n plus d times k log nd, let's say. Okay, yeah, that's actually what you see empirical. Okay. Any other questions? And I mean, you can clearly the error has this nice geometric rate, as long as your x is not pathological and the theta entries are chosen at right. Okay. All right. And there's a lot of work on this problem. Like, how did this chosen at random is a strong assumption? How do you get around that? It turns out that, as long as the entries of theta are kind of well spread out, if you think of it as a graph, if it's like some nice expander graph, you can still get this guarantee and so on. So there's a lot of work around this problem. Okay. Now, let me also say one other thing, which is low rank approximation. Okay, so nowadays you also have this thing called low rank approximation, which is used for fine tuning large language models. Right. So the underlying principle is the same. It's very difficult to work with full matrices. So one of the simplest assumptions you can make about to avoid this bottleneck is to assume low rankings. Okay. So in many large language models, for example, I might have you have this different layers. And if you don't know exactly what they are, basically just think of it as someone computed something after spending billions of dollars or a lot of compute time, and you get some model, like let's say maybe something public like Llama or DeepSeek, and you have a bunch of layers like this. Okay, but this is trained for without any specific task in mind or some specific task. Maybe I want to fine tune this model for my own data set or for my own um, thing. So adaptation. So how do I adapt it or fine tune it? So what's become popular is to start with this as our base weights, and then you update these weights by running rounds of stochastic gradient descent on your small data set. Okay. How do you adapt it? You just assume that I'm going to make a low rank update. Right? So you're freezing the base, and your parameters, new parameters that you're adjusting are only these things, which are essentially like rank 1, rank 2, or something, as simple as that. Okay? Because of that, you can scale much better when you're fine-tuned without having to spend as much as you would to train the full model. Okay. All right. Okay. So that's about SVD and how this notion of low rank itself is quite useful in many different contexts, right? So next, what I'm going to do is kind of put these things aside uh, and talk about a very different topic, which is privacy in ML. Okay. So far, we've taken kind of, okay, I don't care about any other considerations in building my models. My only things are you gave me an optimization problem, I'm trying to solve it, right? Now, we are going to ask other questions related to building models. We're still not going to address the statistical things like, okay, what makes a good model? Would it generalize? Would it work well on unseen data and so on? We're going to talk about other sort of let's say, constraints not tied just to performance. Okay. And in fact, one of the biggest, let's say, shot in the arms for this area was related to matrix completion. Okay. In particular, uh, Netflix Challenge 2.0. Okay. So, the first thing that, the matrix completion Netflix Challenge in 2007 or 8, I forget the year now. But anyway, so that was like $1 million to get 10% improvement, right? Then, some teams won, and then Netflix incorporated this into their recommendation system. Okay. After a year, they said, okay, now that we have gotten this 10% improvement, they did some further things and said, okay, here's the next version of the challenge, which is the same exact, releases few ratings. Okay, and they had a holdout data set as well. But this time, if you bet they got more confident or whatever, or like the publicity, they said, if you beat our model by 10%, then you get $10 million. Okay, so the prize money increased from 1 million to 10 million, but they updated their model, so they thought this would be more challenging. Okay, but this was only live for a little bit, and then Netflix had to cancel it actually. Okay, why? Someone found out that there are some very strong privacy violations in how they released it. Okay, so basically they released it and then they had to cancel it. Okay. So at first it looks kind of weird in privacy violation because when they release this matrix, there are no usernames and the movie names are anyway public. Right? There are no usernames associated with any of the roles. So what does it mean to have a privacy violation? Any guesses? Exactly. So this is in fact was a paper that came out in 2008. So they did it for the first version of the data set. Some of them didn't realize the impact and went ahead with 2.0, but by then I think there was enough public outcry so that they canceled it. So the Netflix data set, as we discussed, was only 1% of the entries being shown, right? So you have very few entries. You have users and movies. Okay. So what Netflix did was, removed any notion of IDs associated with this user. There are no names, no information other than, okay, here's a matrix, the movies are this, and that's it. Okay. And I think even if they had anonymized the movies, it wouldn't have mattered for the same reason. But anyway, so a couple of researchers, Arvind Narayan and Vitaly Shematikov, no, not from UT Austin, they ran what you suggested, which is, what? Netflix is not the only data set that's actually available for users and movies. There's something that's publicly available, like IMDb ratings. Okay. So they said, let me download all of the IMDb data set. Okay. And you had the same thing, users and movies. Right? Some of these users actually use their own names. Some of them were still like, made up names. It doesn't matter, but some of them at least were actual names. Okay. Now, what they said was, they did some, more sophisticated things. But even something as simple as, okay, what I can do is try to identify, let's say all the usernames are jumbled here, and here also it's anonymous, so it's jumbled. But it would be a privacy violation if I can match up the users, right? Because not everybody here is anonymous. Someone actually gave up their names, right? Or maybe they use the same username on Reddit, and then on Facebook and so on, right? If I can correlate, even if I don't know the exact name, as long as can I track this identity across different data sets, that's a violation. Okay. And what can you do? Let's say that's my goal. What would I do? I want to match up users across these two data sets, even though the rows are kind of permuted. Any suggestions? Yeah, even that actually identified people, right? So somehow the fact that our ratings are not as unique as, or rather, the exact numbers are kind of unique identity. Okay, maybe there are many people who would rate these movies like I did, like 4, 4, 4, and so on. But if I take maybe some few movies, then across those, there will be very few people who will have the exact same matches. Right? These two are on different scales. This is on 10, this is on 4. Maybe there's baseline differences and so on. But you can adjust for all of those things. Even a simple processing and trying, and then you can use more sophisticated algorithms, like trying to identify some fingerprinting techniques and so on. Okay. But at the end of the day, they could match many users. Okay. And they could even do this for users who are, in some cases, even for people, for like on the Netflix side, there were only like 4 or 5 movie ratings. Okay. So that's a big violation, and something that Netflix did not think would happen because there are these other data sets which are there, right? But once this data is out, you cannot undo it. Everyone can download it, everyone can correlate it. So that was the problem. Okay. And then because of this, they had to cancel this 2.2. All right. So that's example one. One of the first sort of, I would say, at least in terms of big tech companies trying to organize these computations, and basically something unintended happened. Okay. And the other thing, there are many examples of this. Let me state one more. And this one is funny as well. I mean, okay, I shouldn't say funny, but it's kind of bad. So Massachusetts state government said, I want to release information about insurance and, kind of the medical data that we collect for people to use in their research. Okay. And typically, if you think of data, let's say, for each user, you have some clearly identifiable features, maybe name, email, address, date of birth. Think of it as like a giant database, right? I have a table, for each user, have name, email, address, date of birth, SSN, and then maybe you have stuff that could be actually useful for medical research, right? Like, for example, what are their, height, weight, and then various markers, right? Diabetes. I'm just making these things up, but things like this. You can easily imagine that this portion would be useful to have for someone, forget people who are trying to be malicious. For people who want to actually use it, try to build models. You want to give some risk assessment. If you have so much weight, so much height, so many other characteristics, you want to predict, okay, what is the chance that they will have some risk factor? Very important research, right? So they said, okay, I'm going to release this. And the way I'm going to do it is to basically remove these columns, permute these things, and send it. And that's the data that they released. Okay. And people were, I think computer science engineers and scientists were warning them, okay, this is risky, don't do it, and so on. But then nevertheless, they did it. And someone got so frustrated that they just sent the governor at the time was William Weld, and they posted their own medical record to that governor. That makes sense. So basically, they reconstructed from this table which of these rows belongs to the governor, and they emailed or sent it in mail to the governor. Right? So this is basically saying that even if you remove obviously identifying information, it's not enough. Right? Again, you can correlate across data sets. This is not the only data set in the wild. It cannot work under that assumption. Okay? So William Weld, data was recovered. I mean, you got to appreciate some humor here. Anyway, so so these are called reconstruction attacks. Okay, meaning somehow I'm trying to recover, you anonymize the data in some way, or you thought you anonymized the data in some way, but I'm trying to reconstruct the identity based on this. You can also think of other reconstruction attacks. For example, maybe it's kind of the same thing. I don't release height and weight. I release the rest of the information, but I can infer height and weight maybe. Okay, based on other data sets and so on. All of these would be violations. Okay. So now the question comes, and we do not want to give up on using this data set for medical purposes. Right? And you can't say, okay, I'll keep it in-house and maybe I'll protect it by putting a cage around it. That's also not going to be foolproof. Right? So you need something much more well formulated to define and then guarantee privacy. Okay. All right. So that's what we're going to talk about. And I should say, so far we've been treating kind of analysis, proofs, and so on as ways to understand how these algorithms are doing. And in some cases, trying to come up with the proof is how we got to that. Okay. But for privacy, everything is flipped. Proof is the privacy. Okay, you cannot prove without you cannot prove empirically that something is secure. Okay, you have to actually show or explain why. You have to come up with a proper model, and then formulate your threat models, and then show that I am protected against these threats. Maybe you'll come up short later on in terms of your threat models, but you have to come up with your exact things that you're trying to protect against. Okay. Otherwise, it's just like, okay, I anonymized it, I removed the usernames, I'm done. That's not good at all. Okay. All right. So that's our next topic, which is privacy in ML. And I should say the main punchline is unlike many other things in ML, it might be a weak model that you're protecting against, but you have to come up with the exact specification. Right? Does it make sense? Okay, you can't just say I anonymized it, I'm done. Maybe that's what you're doing, but come up with things saying, okay, I anonymized it. If there's no other data set in this world, then I'm protected. Be precise. That's very important in the context. All right. And we'll talk about this over several lectures. But first, let's maybe just think of all kinds of sensitive data sets. Okay, so give me some examples of sensitive data sets that you would like to be available to researchers, scientists, and so on, but you have to be careful in how you make it. Yeah, for sure, GPS data, right? I mean, just imagine Google suddenly decides, oh, there's this other company which has amazing algorithms for predicting traffic. Should Google just send their data to them? We will be very worried if they did that. Or if it gets publicly known that they're doing that, right? Because who knows, what the other company can do. Even if it's anonymized, they might recover who is going where, right? Other examples. Finance data, definitely. And sorry, app usage time. In fact, that's a very this one at least theory has caught up to practice. We'll talk about that later. Like, Apple implements some of these things which guarantee privacy for app usage time and other statistics that they collect. Okay. What else? Sorry? Yeah, that too. And one big, I would say by and large, the biggest sector where you have to protect against privacy is, yeah, medical data. That's where, in some sense, there's a lot of urgency in trying to build these models, making the data available, but where are the biggest concerns for privacy? Okay. There's a very good demand, very justified demand for making these things public, but at the same time, there's also very strong reasons to have privacy there. Okay. And genetic data again is very important. Nowadays, there's facial recognition, so on and so forth. Okay. I mean, there are other things that you want to keep in mind, like messages, for example. I don't want, all of the messages that a group of people send to each other, like an organization, somehow if they get leaked, that's a big breach, right? All I would say, I think this you can solve with a different set of tools than these problems. Okay. Messages, you can use something like end-to-end encryption and other stuff to try and protect it, where even if it kind of goes into public, unless someone takes screenshots or something, you would be fine. But this other stuff, you really want to make the data set available. That's when difficulties arise. Okay. Okay. So like for example, Apple, for instance, collects which words are the most used in typing and so on, right? But they do it in a way using the tools that we're going to discuss so that it guarantees some privacy. Maybe it's a model that you think is too weak, but the point is that it's completely specified. Here's a model, here's the guarantee that I'm getting. Okay, even if it is weak, it's most important to have exact specification. Okay? All right. And You should also distinguish the kind of privacy that we are trying to get from or protect against than from other breaches where entire data sets get hacked and leaked. Okay, we're not talking about protecting against those things. Okay, we are more concerned with things like releasing the data set without knowing how it might affect the privacy of people participating in the data set. Okay, that's very different from, for example, someone like, let's say, hacking into Facebook and releasing all of the data there, right? Or Facebook sending information to Cambridge Analytica or something else. Okay, that's not going to fall under the purview of the set of tools that we are going to discuss. Okay, all right. So the switch here, I think it's related to what I just said. We're not going to address these other challenges. Is let's think of why people who are in control of these data sets would like to make it public in first, right? The reason they want to make it public is that you expect other data scientists or researchers to use it for something. Okay, so that's kind of how we're going to get privacy. We're going to assume that they want to do something with this data set, and we're going to provide tools for them to do that without violating or guaranteeing some kind of privacy as we define. Does it make sense? It's going to be somewhat specific in how what kind of functionality we are going to allow. Okay. So let's think of our first example. In fact, this is again a very old example, has been used in practice for many years without people realizing exactly or formulating it exactly in the same language. So let's deal with a simple problem, which is extremely simple. So let's say you have person 1, person 2, and so on. And each person has some attribute. And for simplicity, let's just assume it's just a single value. Okay, we'll see how to generalize it pretty soon. But let's say it's just some indicator. It could be something like whether or not that person has a specific genetic marker, or whether or not that person's income is above some level, or whether or not that person has some protected characteristic or not. Okay. And maybe you're interested in knowing, this could be like, let's say, the people living in some zip code, and you want to know, okay, in this zip code, how many people are there who have this specific attribute turned on. Okay, you can imagine this could be very private information that you don't want it to be known for everybody. Okay, but nevertheless, knowing the average would be very useful for various applications. So what we have, I can do an estimate. Our goal is to estimate or calculate the average, which is okay. All right. So how would I, what are ways where I can somehow gather this information while still guaranteeing some kind of privacy? That's what we're going to do. Very simple example, very specific use case. Okay, does the problem make sense? I want to know or compute the average value of some characteristic in some database without revealing too much information about the individual attributes. Okay. And one such mechanism was actually proposed and used a lot by Warner in 1965. Okay, and what he introduced is called randomized response. Okay, so in randomized response, what Warner suggested is, if I'm only interested in the average, while I want to keep some uncertainty about the individual characteristics of each person, what I can do is basically query each person, but then what I release isn't the actual xi, but some randomized version of xi. Okay. So for each user I, you output xi bar, which is xi with probability half plus gamma and 1 minus xi with probability. Okay, this gamma is some parameter. If gamma is a half, then you're basically releasing the entire data set as it is. Gamma is 0 and just outputting random values, so full privacy. There's no information about the xi contained in what I'm releasing. Okay. So if my original thing was x1, x2, all the way up to xn, then I'm releasing x1 bar, x2 bar, up to xn bar, right? And I'm doing this for each user separately. For each xi, I'm kind of flipping a coin and then, or randomizing separately. All right. Okay. And so this is gamma equals, excuse me. This is gamma equals half. And this is randomized response. Okay. And if gamma equals 0, you have full privacy. There is no dependence whatsoever on the original data set. Yeah. You can do, right? So we are exactly going to quantify what you can learn and what you cannot, right? So it's okay to not have privacy. The goal of privacy is not to get, maybe you won't guarantee full thing, but the goal is to quantify what you're guaranteeing. Okay. As long as you have a good model for this is what I'm achieving, I'm happy. Or at least, that should be a bare minimum. Okay. That's a good point. Like, if I do this, this gives me some notion of privacy, but it's like, even with gamma is small constant, that means I'm getting some guess on what the true value is, right? But that's exactly randomized response. This has been around from the 1960s and is actually used in many fields, especially in social science and so on. When they release these data sets, they do apply randomized response and then release the data in surveys and so on. Okay. Any questions? All right. So this is how I'm releasing the data set. And now we should ask, how do I use it for my inference purposes? So there are two things. First, you have to describe how I'm going to modify the data set. The second thing is I might have to even specify how you would get around what you did to answer the original questions that you wanted. Okay. So for example, the next question that we should be asking ourselves is, how useful is the new data set? For example, can I get a good estimate of the true mean? Okay. So, the data set you can use for many things, but let's just gauge how it gives you some confidence in computing the mean. Okay. So if I release this information, how would you guess the mean? Any guesses? Yeah. Right. So, I mean, the mean could have been biased to begin with, right? This could have been, even if it was already like 90% likely to be 1 for each entry, the randomized response is going to change that. Right? So you need to do some correction for the new mean. Okay. So that's what we're going to discuss next. And that's basically a simple calculation, right? So if you think about it, so we have xi bar is xi with probability half plus gamma, 1 minus xi with probability half minus gamma. So if we calculate the expectation, this is half plus gamma times xi plus half minus gamma times 1 minus xi. Okay, which is just okay, which makes sense now. If gamma is 0, the expectation of the new random variable is just half. It has nothing to do with the original xi. If gamma is some small constant, then this will be, there'll be some presence of xi. Okay. So reversing this, in other words, xi, I can write it as okay. So if you had to estimate the mean, I can use this formula. So x1 plus up to xn divided by n is the same as the expectation of okay. So from the new data set, I would compute the mean, kind of correct for the bias I'm introducing, and then scale. That's a very good question, and we should expect gamma to be released with the data set. In some sense, we are setting gamma based on how big we think the data set is. Okay, so we'll talk about that soon. Like, how do you choose gamma? It depends on how big we think the data set is. If the data set has 1 million people, then to compute the average, I can choose gamma much, much closer to 0 while still getting the utility that we want. Okay. So this is the estimate on the released data set. Okay. So this is the correction. And going back to your question, how useful is it? And how do you set gamma? What kind of privacy you get? You can quantify it. And you're not going to show this. This is like some stat 101. You have to compute some things, do some Chebyshev inequality. But if I call this the true number p, in this computed one p bar, okay, And the expected value of p bar now is a true value. Okay. But p bar is like a random variable because what happens for each xi has some randomness in it, right? Over the randomized response, that's the expectation. But for, I do one randomized response, I get p bar. Okay, I can calculate it. How close are these two things? They're close in expectation. I mean, the expectations agree. But you can also show some kind of tail bound to say the chance that my estimate p bar is far from p is small. How small? It's exactly this much. Okay. I'm not going to do this calculation. Let's just take, because we'll do other things which will be more useful later on, right? But this is saying you did this randomized response, you computed a new value p bar, basically computing the average in the new data set, correcting for the bias you might have introduced. How close is to the true average? It is close as long as, as much as this, right? So now it makes sense, right? If gamma is high, then somehow your probability is better. Okay, does it make sense? As gamma decreases, you're kind of introducing more noise into the data set. So there'll be more chance that I'm away. But it's mitigated by how big of a data set you have. Okay. And this is a theme that's going to keep showing up, that depending on how much privacy you want, you might start requiring bigger and bigger data sets to want that much privacy. If I have only 10 people data set, then I have to release the average. There's not much I can do. Okay. At the same time, if a million people have to release the average, I can probably do that better than I could do with 10 people. All right. So in particular, let's say I want, suppose I want epsilon accuracy with at least 75% chance. Okay. There are two parameters here. There's the accuracy that I desire and the confidence that I have that I will get that accuracy. To do this, we need so if I want epsilon accuracy, then I need with 75% chance, then we need this quantity to be at most 1, which means that my gamma must be at least something, or in other words, the size of my data set should be at least 1 over gamma squared times epsilon. Okay. Does it make sense? So we are thinking of epsilon as measuring the accuracy, gamma as measuring the privacy. And we are saying, if I want this much accuracy and this confidence for privacy, then my data set must be at least this big. Okay. Okay. So in general, we would like to find a way to quantify privacy and to know how will it affect the accuracy. You can think of it both ways. How will it affect the accuracy? Or if I want this much accuracy, how big should my data set be? Okay. And that could depend on the algorithm. In fact, we will see that the kind of privacy that you get from this is the following, right? So randomized response means that with some chance, my value is not affecting the data set at all because it's getting flipped completely. Okay? So that's the kind of privacy that we're going to quantify. And then the quality of a private algorithm will depend on how big a data set you need to get that level of privacy. Okay? And we'll say different algorithm which will do better than randomized response. So randomized response has been around since the 1960s, but there's a slightly different one which gives you better guarantee. All right. But to do kind of this comparison about which algorithms are better than each in general, and how to compare two algorithms in terms of privacy, we need a language to talk about all of this. And one model that has gained traction over the last few years and is quite nice is differential privacy. Okay, it's a very formal model. As I said, one of the main contributions of privacy, whether you might be satisfied with it or not, but the minimum and most important requirement is that you have a precise model and formulation of what you're guaranteeing. Okay. And then many versions of differential privacy. I'm just going to call it differential privacy for this lecture series, but technically, this is really central differential privacy, or sometimes also called the trusted curator model. Okay. All right. Let's take a couple of minutes break, and then we'll come back and talk about this. Okay. Okay. So as I said, there are many different versions, but we're going to talk about the basic version, which technically is the central differential privacy model. And one way to think about this is it's very user-centric. In some sense, what we're trying to do is to give some confidence or guarantees to individuals to help them, in favor of participating in your data set. Okay. So imagine some company comes and says, hey, I would like to share your data set, share your data in this data set I'm releasing. Would you agree to it or not? Well, this is what, if they say, okay, I'm implementing differential privacy and this is the exact things that I'm doing, maybe it will give some clarity to them on how their data can be used. Okay. So if you think about at the user level, each user is getting some confidence in how their individual record is going to be used. Okay, or what kind of privacy they can expect. It's not for the entire thing. Okay. Does it make sense? Okay. So let's formalize it, and perhaps it's clearer if I just state the formal model. So you have user one, and right. So we have n users. Each user has their own record. It could be their entire medical history. It could be the genetic data. It could be their demographic information, their financial data, or whatever. Okay. And then you have some, let's say, ML algorithm. Maybe it doesn't have to be such a big box. It's just some box. Okay, we have some ML algorithm, which is on this side. And the ML algorithm would like to use the individual records to do something with it. Maybe make some prediction, build a model, or whatever else it wants to do. Okay? And we are going to imagine that there is somebody sitting in the middle, a curator, a trusted curator. Okay. Maybe this is better. Okay. Now, so the ML algorithm is going to give a query to the curator, and then the curator is going to talk or look at the data set and then give an answer. Okay. And this process repeats: query and answer and so on. Okay. So this is both literally and figuratively a caricature. The actual thing can be much more nuanced. But let's start with this basic setup and we'll see what kind of things we can do. All right. And we'll be as general as possible with modeling users' data. We'll just think of it as some database of values, and there are n records. Okay. Each user record could itself be a vector, could be a single number, could be kind of, whatever else you want. Let's just put X for that. Okay. And then you have n records. Okay. And in differential privacy, the fundamental algorithm or primitives that you're trying to construct are what are called mechanisms. The mechanism M is a function which takes the database and returns a value, y, which you should think of as answer for the query, like a label or whatever you want. Okay. So this is databases. For example, this themselves could be vectors or n collection and a collection of n vectors, or this could be answers for a specific query. Okay. So for example, you can imagine, I had a collection of users' data, their demographic data, their income data, the zip code data, some genetic markers, and then first an algorithm comes and says, okay, can you tell me the average age in this group? That's one query. And one answer could, maybe you will use randomized response to output the average age. Then another, maybe the same algorithm comes and says, can you tell me the average income, average height, average weight, and so on? Okay. So for each query, you can use some algorithm to give a potential answer. All right. Does that make sense? And for example, I could use randomized response separately for each query. Yeah. So that's a very good question, and you cannot make very or at least you have to characterize privacy in terms of the kind of queries you allow, right? If I allow very specific queries, I can say, okay, give me the age of the person at address. Okay, so then how do you get privacy for that, right? So you need to come up with some model for what kind of queries, or at least say that, okay, if my queries satisfy some property, I'm going to get some privacy. Okay, and the properties that we'll ask for will be reasonably nice. Like as long as they're intuitively smooth, I should be able to do something. If they only depend on one person, or like, okay, tell me the income of person who is 36 years old, lives on this, I'm not 36 by the way, but on this specific street and so on, then that could easily lead to a violation. Okay. But the goal is to quantify exactly what kind of guarantees we're going to get. All right. Okay. So the way to think about the mechanism is it takes a database as input every time right? And then sends some response to the ML query algorithm. There is utility that we have to quantify separately. How useful is the output of the mechanism? You know, one way to get privacy is to just, no matter what the ML algorithm asks, I can just say 0.1. That guarantees full privacy, but it's not very useful, right? So we'll task, kind of really address both of these things separately by basically coming up with a definition of privacy and then looking for mechanisms which satisfy this definition while being as useful as we can make them. Okay? You can think of it as two knobs. Either you fix the utility and then ask for the most private thing that you can have, or fix the privacy and ask for the best utility you can get. Okay? Both are the same thing, but it's helpful to fix the privacy in some sense. And how do we define privacy or differential privacy? Okay. As I said, the basic notion of privacy here is in terms of an individual user, right? And the privacy requirement is going to be that if I look at the mechanism's answers, I should not even be able to tell if a specific user is in the database or not. Whether I participated in this survey or not should not be, you should not be able to deduce that based on the interaction with the mechanism. Okay? If you're not even able to tell whether I'm in the database or not, then you cannot tell what my individual features are. Okay, does it make sense? Okay. And the way to make it precise is to use the notion of indistinguishability that is very powerful and commonly used in cryptography. Okay. So in particular, we'll say, okay, take any database and maybe I'll replace in first database, the last user is Alice. In the second database, the last user is Bob. Every other record is the same. Only one record has changed. Okay. So we will call such databases neighboring databases. All records are the same except for one. And the property that we want is that the outputs in both cases look similar. They should be statistically indistinguishable. Okay. So let me write it down formally. In fact, we'll ask for something even stronger than statistically indistinguishable. So if I have two databases, we call them neighbors if they differ in only one row. Okay. And the idea, the intuition is that we want to say the mechanism is private if the distribution of M of D and M of D prime are very close to each other. The set of answers that you would see under one versus the other, you cannot tell them apart. Okay. Now we're almost there formally, except we need to quantify what this distinction is. Okay. And how would you, what are some ways to characterize this closeness? Any guesses? But they need not be like a single 0 or 1 value, right? There could be multiple values in there. Any guesses? What might be other ways? Yeah. Right. So that's like statistical distance, right? Between the distribution of M of D and M of D prime. That's almost good, except in privacy, you have to worry not just about the most probable outcomes, but also protecting the privacy of the unlikely outcomes. Okay. So it's typically we are okay with approximate answers, but for privacy, the biggest violations happen for the minorities in some sense, right? The things which are rare, that's where you can get privacy violations, right? Like for example, maybe you have a database, two databases, and one person's income is like $1 million. Everyone else's income is like $100. So most of the time, you might protect the privacy, but there's a rare chance that you might not. Okay, but that's a significant violation for that individual. Okay, so in some sense, you're also not. So that's the reason you don't just look at statistical distance. You try to look at a different metric which tries to protect against even for rare events. Okay, and that's a very important notion. Like coming up with this exact definition, people tried many things, but it turns out that this is the right one. Okay, it took a while for people to come up with this notion. I think it was 2005 or something like that. The paper that introduced this won the Gödel Prize for coming up with essentially for coming up with this definition and then studying properties for it. Okay, so we will say a mechanism which takes a database and releases values is epsilon differentially private if for all neighboring databases. Okay, and any possible answer y. Okay, for any two neighboring databases and any possible answer y, the probability that I would output y in one database is almost the same as the probability that I would output y under the other database. Okay, and here close means that it's traditionally written this way because it makes for some theorems to be stated kind of composed better because multiplying is easier in the exponent. Okay. For any event y, the chance that M outputs y under D is at most e to the epsilon times probability that I would output y under the neighboring database D prime and vice versa. Okay. Essentially just think of e to the y as e to the epsilon as basically 1 plus epsilon. Okay, you could have put 1 plus epsilon and kind of had the same thing, but this turns out to be quantitatively much better thing to try. Okay. Does this make sense? Okay. So this asking for this multiplicative guarantee per any possible output. That's what makes it different from usual notions of distances. Like it's not statistical distance. It's something a bit more refined. For every possible outcome y, you should have this multiplicative guarantee, which makes it much more important for rare events. I mean, this distinction is much more important for rare events. Okay. Yeah. It's strictly, I mean, it gives you epsilon close in statistical distance. Okay, because you can add up everything and then you can. Okay, so another way to visualize this is basically maybe I have one database, D, and maybe this is my other database, neighboring database, D prime. Okay. When I run the mechanism on it, let's say I'm asking for, the output Y is integers. The labels, what the mechanism outputs are integers. Then I can write down some kind of histogram for the probabilities that I would see 0 under the mechanism. The probability that I would see 1, the probability that I would see 2, probability that I would see 5, and so on. Okay. Maybe the others are 0 here. This is 1, 2, 3, 4. Okay. And I can kind of draw the same histogram under D prime. Okay, something like this, right? What differential privacy means that for every one of these values, these heights are multiplicatively close. Okay, so in particular, if something is 0, it should be 0 in both. Like a rare event, like if something is never even and you suddenly see an even number, even if it's very unlikely, that would be a complete violation. Okay, so that's not allowed. That's the point. Green is not particularly visible. Maybe I can do this. Right, so heights should be within e to the epsilon factor of each. Okay, again, e to the epsilon is mainly for convenience because when you multiply, it becomes nicer. But it's really, think of it as like 1 plus epsilon. So epsilon is like 0.1 or something. Okay. Any questions? All right. So this definition seems kind of, strange and in some sense strong because the fact that you require this for every possible output Y, no matter how unlikely, is a strong constraint. Okay. We'll see later on how to relax that. But just to kind of, give a sense of how useful it is, the US Census Bureau used it for the 2020 census. Okay, for all of the data that they collected, US Census does this thing, this big thing for every 10 years. Okay? And they release information about this, about various demographics, and this helps determine all kinds of very, very important factors. And they explicitly use differential privacy. I forget what specific epsilon that they use. But the way they implement, now when you interact with this data set, you are going to go through differential privacy. Okay, they're going to interact with the data set through a mechanism which guarantees epsilon differential privacy. Right? And Apple uses some form of differential privacy. It's not exactly central. It's something called distributed, but basically they want to collect, what is the most, popular app. When I'm trying to enter a word, it does autocomplete, right? The autocomplete can change over time depending on what word is very popular now. Okay, so this information is being collected by Apple and then being used in their models, right? But it's being used through differential privacy. It's not storing the raw counts. It guarantees differential privacy. So whether or not my data is used for this prediction, it can only change all of these things by this 1 plus epsilon. So this is the guarantee that they're giving. And then, you choose, well, okay, is this satisfiable for you or not? Okay. And the point is that there is a quantifiable guarantee that you can get. Same for Google. And to some extent, Microsoft also uses differential privacy in some of their products. So Google uses other forms of differential privacy for AdWords search and so on. Okay. All right. And just qualitatively, small epsilon is better privacy, of course. Okay. And typically something like epsilon being 0.01 is satisfactory, I think, for many empirical purposes. And the other thing, which is, people have studied ways to get around this, but this is worst case for all databases. Okay. We're not saying that I'll preserve the privacy for typical databases. We have to guarantee privacy no matter what the database is. Does it make sense? Like, maybe for typically, if a sample is set of 100 people, like let's say I take a hospital and I want to release the data differentially privately, you might say, out of 1 million people, maybe the subset of people who come to me is coming from some random sample, and then I give privacy and so on. That's not allowed, at least under this definition. No matter who come to your hospital, which 10,000 people, maybe for some reason, the set of people who came to your hospital is extremely kind of concentrated in some zip code, which is not unlikely, but even then you need to guarantee differential privacy. Okay, you're not allowed to make any assumptions on D, at least in this full model. Okay. All right. So now that we have a formal definition, or at least one formal definition, let's go back and ask how to implement just the basic one, which is computing the mean differentially. Okay. So now we have a model and we have a very precise algorithmic question as well as a result of that. So we have a database, user 1, user 2, all the way up to user n. And let's just imagine, each user has a single attribute, right? And we have our curator sitting in the middle. Looks sadder for some reason. Okay, this is our curator sitting there. And then, someone comes and asks, okay, what is the mean? And the curator has to answer something. Okay. As I said, even though this looks very simple, this actually, if you implement this properly, you can use this as a building block to do full-scale differential privacy from even, very sophisticated ML systems. Okay. Because, just kind of jumping ahead, for example, let's say I'm trying to do ERM. You can think of it as a case where every round, every step of gradient descent is like a mean computation. I need to compute the mean gradient. So if I can generalize this to vectors, I can use this as a plug in between to get a guarantee for the entire model, perhaps. That requires extra work, but this is not just a toy problem. Okay, if you implement it properly, it can help solve even bigger things. Okay? All right. So we want to build a mechanism to compute some function. In this case, the function is the mean. Okay. And okay, we will, so we already saw one possible mechanism, which was randomized response. Okay, that was one way to do it. But we can now, we should go back and ask, okay, what kind of differential privacy does it give you? What epsilon does it guarantee? Or thinking other way, if I want epsilon differential privacy and I'm going to use randomized response, how much noise can I add? What is the utility? Okay. So you can make that calculation, and we will do that more carefully next time. But the punchline is that randomized response with noise rate gamma, with let's say with parameter gamma is is O of gamma differentially private, and the constant is also just like some 2 or 3 or something. Okay, the smaller I make the gamma, the better my accuracy, better my differential privacy. All right. So let's say we'll show this in the next lecture, but let's suppose that this is true. Yeah. Right. So that's a problem, right? So how it will play out for us is that we're going to assume that our functions, either you have to assume the ranges are bounded, okay? Or the other way to say that is if my function is too sensitive, then I cannot get differential privacy too well, okay? So you have to draw, and we'll make it very precise in some sense. Given my function satisfies some kind of smoothness property, and I want epsilon differential privacy, how big a data set do I need? Okay. So in that case, basically you'll say, the only way to handle that is if my database is already has like 1 million people. Until then, we cannot get around this issue. Okay. So that's one way to think about it. I think that's the most useful way is how big should my database be before I can make it useful and private. It gives you precise trade-offs, right? So in some, okay, so now if I call this epsilon, so this is like O of gamma, and we already said that, if we want, actually, maybe my notation was bad. I should have used, if you want alpha accuracy for randomized response with 75% chance, then we need n to be at least 1 over alpha squared gamma squared. Okay, it's I earlier used epsilon here, but I shouldn't have done that. I should have used alpha there too, but I'm just changing the notation. And so in other words, to get epsilon differential privacy, right? And alpha accuracy with 75% chance, randomized response needs the database to be something like 1 over epsilon squared alpha squared. Like some big constant as 1 over epsilon squared alpha squared. Okay, so if epsilon is 0.01, my alpha is like 0.1, then this is a pretty big number. Okay, until my database becomes that big, I cannot do much. Okay, and we will see that actually there is a different algorithm which can achieve the same kind of epsilon differential privacy, alpha accuracy, but quadratically better. Okay, so once we have this sort of quantitative way, we can talk about comparing algorithms. Right? What's the best algorithm for getting epsilon differential privacy and alpha accuracy? So that's kind of going to be our algorithmic question next. Okay, so we'll start talking about that. And sometimes even for specific functions, it's very important to develop algorithms. Depending on what the function is, like if the mean is high dimensional, if the function is high dimensional mean computation, that's a very useful function because you can use that as a subroutine to do many other things. Okay, but by and large, we'll talk about general classes of functions, mainly characterized by smoothness, and then develop mechanisms for them. Okay, if the function is very abrupt and it changes dramatically when a single entry is changed, it's going to be very difficult to get utility for that function. Okay, the function is one if and only if a person named Raghu Maker is inside the database, then forget privacy for that. Right, the only thing you can do is give random answers. Right, because and that's makes sense, and smoothness is a good way to quantify that. Okay. All right, so we'll talk about this on Monday next week. Wednesday is the exam. So the exam will be 1 hour 50 minutes, starting from 12 to 1:50. Okay? All right. See you all on Wednesday.